Hi, I'm Ryan Baker, and this is the penultimate video of Big Data in Education. Today we'll be talking about reinforcement learning. Now, reinforcement learning is different than most of what we've studied in this MOOC. Most of what we've studied has been about an algorithm learning information, which perhaps then it shares with us clueless humans. And some foundation models are an exception to this, some of them do other stuff. But this session, reinforcement learning, is about an algorithm learning what to do. Cheyenne Dorody defines reinforcement learning as follows. In reinforcement learning, the goal is for an agent to learn a policy, a mapping from states to actions or probability distributions over actions that incurs high reward. The policy specifies for each state what action the agent should take. There are multiple frameworks for reinforcement learning. Three core ones that I'll discuss today are multi-arm bandits, Markov decision processes, and its variant, partial order Markov decision processes, POMDPs, and deep learning. The first I'll discuss is multi-arm bandits. The base case of multi-arm bandits is as follows. An agent needs to make a sequence of actions. An agent needs to make a sequence of choices. The goal is to maximize quote-unquote reward over time based on the experience. And reward is anything we can assign better or worse numbers to. There's a set of possible actions, call it A, finite and typically small. There's one action per decision point, called a round. Each time an action A is made, a reward R of some level is received, and the reward is related only to the action. In this model, all rewards are independent from each other and any other factors, and there's no contextual or temporal effects. If you do the same thing, you get the same result. Think of it like if you're deciding which of two slot machines to play. The slot machines are going to give you the same probability of a reward every time, no matter what. So, to give an example, my 3-year-old wants me to give her cookies. She can giggle, dance, cry, hit, bite, or poop in her pants. Each action has a different average reward and a different distribution of likelihood. And her goal is to figure out, being a very smart 3-year-old, which action is best. Another example, I want my students in this MOOC to learn, measured by immediate pre- and post-tests. I can lecture, tell a joke, ask a leading question, ask for examples, or assign a group activity. Each action has a different average reward and a different distribution of likelihood. Can I figure out which action is best? Within these multi-arm bandits, because the result is not going to be exactly the same every time, even though there are no contextual or temporal factors, a balance has to be struck between two things, exploration and exploitation. Where exploration is saying, I'm not sure what the right answer is, so I'm going to try something that doesn't currently seem best. And exploitation is saying, I know which approach is best, so I'm going to use that. And the balance and choice at any given time between exploration and exploitation depends on how certain the bandit is about the reward each action is likely to give. Moving on from just the straight-up multi-armed bandits are contextual multi-armed bandits. Now, a contextual multi-armed bandit is just like a regular multi-armed bandit, except we're going to change a couple assumptions. Instead of saying that the reward we get is completely based just on the action you do, some other factors, including context, also impact how much reward you get for a certain action. At each round, the agent will also receive a context feature vector, a set of variables that represent the context the agent is operating in. And the agent will then figure out how the relationship between the actions and the rewards depends on context. So for example, let's say that I want my students in my EDM class to learn, I have a set of actions I can do. A contextual multi-armed bandit operating as me would also perhaps know what percentage of students are looking at me, how far into the class session we are, how many students came to class today, and whether it's raining outside. It turns out perhaps that lecture works better earlier in class than later in class, and that a joke works better if very few students are looking at me. Another variant on multi-armed bandits that relaxes another assumption is non-stationary bandits. Non-stationary bandits say, what if the reward's changing over time? What if the circumstances aren't always identical? In this case, it becomes necessary to check for changes in the reward functions over time. Goodness! We were usually getting a reward of 17 earlier, but now we seem to be getting a reward of 12 for doing the exact same thing. In this case, the model is always asking, is the current performance outside the expected range? And if so, something might have changed and we might have to adapt. The second big category of reinforcement learning is MDP, Markov decision processes. MDPs add a key dimension, state. The model now assumes that the environment has multiple possible states it could be in, and the reward for action varies based on the state. This is another way of representing context. Perhaps my class is in a state of early class attentiveness. Perhaps my class is in a state of late class laziness. Let me give another example. Maybe my daughter wants a cookie, but her strategy for getting a cookie needs to depend on Daddy's state. Is Daddy happy, silly, grumpy, stressed out, or just plain busy? Perhaps if Daddy is being silly, dancing is best. That'll get her the cookie. But perhaps if Daddy's busy, she needs to sneak into the kitchen and climb on a ladder and I won't even notice. That totally has never happened. So, a Markov decision process needs to learn more things than a multi-armed bandit does. It needs to learn what the set of states are. It needs to learn the set of transition probabilities between the states based on what the action was. This may seem very similar to hidden Markov models. It needs to learn the mapping between actions and rewards for each state, where state plus action equals reward. And it gets complex very quickly. This is just a few of the many examples that it has to learn for the case where my daughter is figuring out what action to do based on my mood to get herself a cookie. A variant on MDP is the finite horizon MDP. This model adds the caveat that there's a maximum number of steps. Now, this is useful info if the interaction won't go on forever, and it's actually pretty common in a lot of papers and practical applications. The true number of steps is never infinite, but often we don't know it. If we do, some calculations are easier. And incidentally, you might be saying, what makes these models Markov? Well, Markov is named after the person who made this assumption first in this kind of work, and it says that the transition between states takes only the previous state into account, not further back. So now that Daddy's in the state of grumpy, it doesn't matter what Daddy was feeling before this. Knowing whether Daddy will become happy or silly or something else is based only on Daddy's grumpitude. That's a real word. The Markov assumption is also seen in hidden Markov models, aka a previous lecture, and it's used there to model and predict transitions. The next and most common variant of MDP is the POMDP, the partial order MDP. In a POMDP, we can't actually observe the state. We don't really know is Daddy grumpy or silly. We have observations separate from the rewards related to the states, and the algorithm tries to infer the probability of states based on the observations. To give an example, let's say my daughter is trying to figure out my state, to figure out what action to take to get a cookie. She doesn't know if I feel happy or grumpy, but based on my facial expression and my tone of voice, there's a 50% chance of happy, a 20% chance of silly, and a 10% chance of grumpy. Now, sometimes you'll see papers that just talk about Q-learning. Q-learning is the most popular algorithm for fitting the parameters of an MDP or a POMDP. It introduces a time discounting factor with a hyperparameter indicating how much to discount future rewards, and therefore how much to explore versus exploit. It fits a state plus action equals reward function, where it keeps a memory of predicted reward for each state and action combo, and repeatedly updates the predicted reward as new evidence comes in. And classically, that reward estimate is based on a simple updating function. But more recently, deep Q-learning / deep Q networks use a convolutional neural network to fit that state plus action equals reward function, which leads to rather complex functions for determining that. Now, so far, most of the rewards we've talked about have been immediate. Cookie. But in education, the rewards we care about are often not immediate. Immediate performance in a learning system versus long-term retention. Immediate performance versus the student's preparation for future learning. Improved grades or attendance in the short term versus graduating from high school. An example of this is seen in Shen and Chi, where they looked at college students using an intelligent tutoring system. They used a reward either based on immediate student performance or long-term learning using an ensemble of different RL methods. They found that the models were actually quite different, but that when they made decisions based on them, surprisingly, there were no differences in learning outcomes. Another approach to doing delayed rewards is to choose or infer a short-term proxy for the long-term reward, and then evaluate the success of the proxy and the overall approach using the final reward. You tune the proxy and the overall approach using the final reward. An example of this is seen in Zhu et al. 2020, where students used an intelligent tutoring system. The true reward was pre-post gains, but the proxy was 142 features of student performance at an action-by-action level. A neural network was used to predict pre-post test gains for the features, and changes in predicting the pre-post test gains was used as the proxy reward. The policies were induced using proxy rewards and deep Q networks. The paper didn't discuss overall learning differences. You see a theme here. It's often, it's hard to really study the impacts on learning. Even just getting to the point where we're looking at longer term learning has been kind of a big step for the field. Okay, so I've gone over a lot of methods here, and this just scratches the surface. There's tons of different ways to do multi-arm bandits, POMDPs, deep learning networks. There's the same explosion of complexity as is seen in DKT family algorithms. There's algorithms that do multiple passes through the data to figure out a better policy. There's algorithms that use multiple neural networks optimizing different aspects of the overall problem, such as estimation of the long-term reward, selection of the immediate policy, the shift from exploration to exploitation, context, and so on. It can get really complex. Now, it's worth noting that the reinforcement learning from human feedback that's used in large language models is simpler than this. Those systems just use a thumbs up, thumbs down feedback as responses, and this simplicity of reward makes it a lot easier for human beings to give feedback. But there's a lot of potential applications, and correspondingly there's been lots and lots and lots and lots of reinforcement learning papers published in educational data mining and related communities. A lot of them thus far are simulations, totally simulated data, or distillation of policies from real data, but after the fact, not actually using reinforcement learning in real time to make real decisions. A lot of the ones that aren't simulations, a lot of the ones that actually involve making decisions, are still lab studies or mechanical Turk studies. But there are some examples of real-world use. For example, Mandel et al. Looked in the educational game Refraction, which is used by children over the internet to learn fractions. There were 6 mathematical concepts, 4,500 features representing the gameplay, which they distilled to 100 features using a neural network, and then distilled to 2 or 3 features using PCA. They input it to POMDP, and they found that students played the game longer without quitting when the game's behavior was governed by POMDP than by a random sequence or an expert selected sequence. So this was definitely quite a success for reinforcement learning. In another example, Clement and colleagues looked at an arithmetic mathematics game used in schools. They had 7 math knowledge components, and they used multi-arm bandits to select the knowledge component order the student be presented with. Using that multi-arm bandit compared to an expert design sequence, students reached higher levels, they were more likely to complete at least one exercise, and they had higher pre-post learning gains. In a third example, Shen and colleagues looked at an intelligent tutoring system for college logic. Students using the system completed an average of 23 problems across 6 levels across an average of 5.5 hours, and an MDP or a POMDP decided whether the student should complete problems or receive worked examples. And they found that there was better learning for the MDP than a random, but they also found that the MDP did better than the POMDP, and that was a surprise. In a fourth example, Segal and colleagues looked at a math e-learning system for 7th graders. They had multiple practice sessions of 10 questions each, the topics were selected by a multi-arm bandit, and the authors claimed higher learning for multi-arm bandits than the control conditions, but the sample wasn't big enough to demonstrate statistical significance. And in a final example, and I hope this illustrates just kind of the sheer richness of the work in this area, Basson et al. Looked at Introduction to Linear Algebra, an online mini-course for Amazon.com employees. They had 3 skills and 4 activities per skill: video explanations, written descriptions, worked examples, and assessment questions, and they used reinforcement learning to sequence and choose activities to skip. They found a higher rate of course completion for the reinforcement learning-based condition than a linear condition or a self-directed condition. However, learners who completed the course under reinforcement learning typically experienced considerably less content than students in the other conditions. Is this a good thing? Was it skipping stuff they didn't need? Or a bad thing, they were missing stuff? Possibly a little bit of both. They found higher learning gains for reinforcement learning than the linear condition. However, there was a strong appearance of lower learning for reinforcement learning than the self-directed learning condition. If you look at the graph, it looks significant based on the error bars, but the paper claims it's greater than 0.05. So it's not clear whether the reinforcement learning was kind of possibly tied with the self-directed condition or was worse. The bottom line is it still did better than the straight linear. So this concludes our lecture on reinforcement learning. Next up, multimodal learning analytics.